session is a special session on mobile multimedia sensing. So the topic is kind of related to a bit different from the previous session. We combine an element of mobile computing and sensors. No problem. Your time. Okay, so we have 3 talks in this session. So I guess kind of the topics are kind of different. I guess it demonstrate the range and the scope of the possibility in this area. So the first talk is adaptive planar and rotational image stitching for mobile devices, and the presenter will be Christopher Herbon from the University of Applied Science from Gottingen, Germany. Thanks.
Okay, welcome to my talk, Adaptive Planar and Rotational Image Stitching for Mobile Devices. Yes, my name is Christopher, I'm from Gottingen, Germany, and what we will talk about today is 2 different types of panoramic images. These are 2 types of panoramic images that you can see right here, and we will take a look at why they are different, how they are different, and why we need to treat them differently. So let's first take a look at what is image stitching. Maybe not all of you are totally familiar with this. Image stitching is what we call the fusion of overlapping images. So we have a couple of images here. These images are taken from a so-called woodblock file. And we want to fuse these images together into one big panoramic image. So the end result should look like this. So this is actually what we call a planar surface, the surface of this woodblock file. And this is one case of the panoramic image stitching algorithms that we will talk about today. So how does the image stitching work in detail? Well, the first thing we need to do is we need to extract feature points, for example, SIF or SURF features. And then, well, we can see them here for 2 features. Obviously, we would extract the features for all images. And the next thing we will do is we will match these features. So we need to find out which features in one image correspond to the features in the second image. And then we get the correspondences, which you can see marked as lines here. And from these correspondences, we can get the so-called homography matrix, which is a perspective transform. It's a 3x3 matrix, and it tells us how we need to warp the second image so that it optimally overlaps the first image. So that is the homography matrix. And once we apply the matrix, we can kind of overlay these images and we get a larger image. But one problem that we can see here is that you can still clearly see which part of the image belongs to the first one and which belongs to the
question.
Yes.
So, for example, if your first picture is color and the other one is black and white or grayscale, would that still work?
That would still work, yes, because the features are extracted in grayscale domain anyway. So that's.
What about the resolution change? If one of them is higher resolution, the other one is lower resolution.
Well, the features, the SIF features, for example, they are scale invariant, so that's not a problem. It would still work.
So that means that actually I use multiple different cameras to take different features and then still stitch them.
It would be possible. In this case, we use a smartphone. So that's because it's a mobile stitching algorithm, so we only have one resolution. But it would work equally well when using different resolutions. So the next thing we do is we adjust the brightness and remove some artifacts, and then it will look like this, so you can't really tell anymore where one image begins and where the other one ends. So that's sort of the process of image stitching. But now we need to sort of take a look at the context, because as I just said, we want to apply this image stitching for mobile devices. That is possible because the mobile devices now, as you all know, feature very powerful processors that are capable of such an exhaustive task. On the bottom you can see, for example, the iPhone image stitching application. So most modern smartphones actually feature such an algorithm. The problem here is that these are only exclusively rotational panoramas that you can produce. And we will shortly take a look at what the difference is between rotational and planar. So let's take a look at the problem and the literature so far. As I mentioned, we have two types of panoramas. The first one is the planar, where we take images of a planar surface. This could, for example, be a wall or also maybe microscopic data, but we will use this planar panoramas on smartphones, so you would probably use it in like an urban environment where you can take pictures of the wall. And you would actually have to move the camera, so there is a translation in this case. For the rotational panoramas, this is not the case. The camera center stays stationary, and all we do is rotate the camera. So that is what you all know. When you take a panorama, you sort of do this rotational motion around one axis, and these panoramas are different, and we need to treat them differently. But only from the images, we can't really tell so far how they are different, and we will take a look at how we can distinguish these types of panoramas. Okay. Another problem that we have is that the planar panoramas, they should always be mapped onto a planar mapping surface. That's what we would expect when we, for example, take pictures of the wall. We want it to be a planar mapping surface. And we need to use the homography's full 8 degrees of freedom. As I mentioned before, the homography is a 3x3 matrix, but we can scale it any way we want, so it only has 8 degrees of freedom. And we want to use all these 8 degrees of freedom when dealing with planar panoramas. On the other hand, when we have a rotational panorama, we want to map it onto a cylinder or a sphere. And we only want to use 3 degrees of freedom, which are the 3 rotation axes. That is what state-of-the-art suggests. This is very important to choose the correct mapping surface. We will see here, for example, this is a rotational panorama which was mapped onto a planar surface. So there are some strong distortions. We can't even fit the whole panorama onto our mapping surface. So this just doesn't look right. On the other hand, this would be the correct mapping, which is a cylindrical surface. And that is, it just looks better to the user. That is what the user would expect. Okay, so the question that we need to ask ourselves is, how can this panorama type be determined? How can we know which type of panorama we have? And in the next step, how can we apply this information when processing the image stitching? Well, literature suggests that we should use the 8 degrees of freedom when dealing with planar panoramas, as I just said. And this work, it's just a selection. It has been done many years ago, so this is not a very new topic. And also we have the rotational image stitching, which uses 3 degrees of freedom. It has also been looked at several years ago, but also recently some advances have been made. And the problem that we have is that there is no work so far that tells us how we can distinguish between these two types of panoramas, or how to know when to apply which type of panoramic stitching. So what we did and what our contribution is, we want to determine the panorama type, and what we need for that is we need to extract the camera motion. So we want to see how the user moved the camera only from the image data. And we do that by a parametrization of the homography matrix. What we get is a rotation matrix and a translation vector. And we do that by saying the first 2 columns of the homography matrix are the first 2 columns of the rotation matrix. And the third column of the homography matrix is the translation vector. Once we have this information, we can calculate the camera center, which we say is C, and that is equal to the negative inverse of the rotation matrix times the translation vector. So we get the camera center. Okay, now what we did is we thought of a model. How can we know when we have a rotational panorama? What you can see here is that when the user moves in a rotational way, all camera centers are within a certain threshold. The distance between the camera centers is not very large, so we can define this threshold, and we can say if all camera centers are within this threshold, then we know it's a rotational panorama. But if there is larger translation between the camera centers, then we know it's a large translational motion, and it's a planar panorama. And in order to determine this threshold, we found that a good heuristic would be the normalized camera width, which we obtain by dividing the camera width in pixels by the focal length. And the second thing we need to do is we want to constrain the user to perform a single row sweep for the rotational panorama. So we need to define a consistent rotation. This consistent rotation can be defined by looking at the optical axis of the cameras, where we say that the angle between the first and the second camera's optical axis must be smaller than the angle between the first and the third camera. And the same holds true for the second and the third camera. So this is the consistent rotation. And the next thing we need to do is we need to select the reference image. This is just to restore sort of a global motion between all of the cameras. Which image we select is does not really have an effect on the outcome, but we need to select one to restore the global motion, and we select the middle image, the center. Now we have the global motion, and our algorithm looks at, are all translations smaller than the threshold? If this is not the case, then we know we have a strong translational motion which corresponds to a planar panorama. If all translations are smaller than the threshold, we need to check if the rotational motion is consistent. If it's consistent, we know we have a valid rotational motion and a valid rotational panorama. If this is not the case, we can abort the calculation and say this is not how we assume a rotational panorama to be taken. So our contribution is the panorama type criterion, which we define as the translational threshold plus consistent rotation. Now let's take a look at the application of the algorithm. As I mentioned before, one very crucial thing is the mapping surface. So what you can see here is a bookshelf C. And the front of this bookshelf corresponds to a plane. So the first 4 images that you can see here have been taken in a translational fashion where the user actually moves the camera, and when stitching this, we get a planar panorama, which one would expect. The second example is the same scene, but in this case, the camera center actually stays stationary. All we do is we rotate the camera, and what you get is a rotational panorama. And you can clearly see the difference here, and you can see why we need to distinguish these types of panoramas. The second application is the bundle adjustment. Bundle adjustment is an iterative nonlinear refinement algorithm that we need to optimize our point correspondences between the images. And state of the art suggests that we should use 8 degrees of freedom when dealing with planar panoramas, and we should use 3 degrees of freedom for rotational panoramas, because it is more robust and it has faster convergence, because the degrees of freedom are we have less degrees of freedom than for planar panoramas. So the panorama type criterion enables us to use different bundle adjustment models. We can use one model specific for the rotational panorama and one model specific for the planar panorama. We conducted some experiments. We have a data set that has 100 images of a panorama, where 50 were a rotational panorama and 50 were a translational or the planar panorama. And the panorama type was determined correctly in all of the cases. I have to mention all the data sets were obtained by a smartphone camera, so we don't have a resolution change and we don't have a change in focal length, but the algorithm would work equally well. So as I just said, the bundle adjustment for the rotational panorama is stated by literature to have a faster convergence, and we can confirm that because it is almost 4 times as fast as the bundle adjustment for planar panoramas. The next thing we looked at was the average reprojection error, which is a measure of how well the images overlap. And average reprojection error was smaller than 1.1 pixels for planar panoramas and 1.3 pixels for rotational panoramas. This is another example of the data set where you can see this is a school wall. The top image was a rotational panorama and the second one a translational planar panorama. Okay, so to draw some conclusions, we established a panorama type criteria which uses the camera motion, and the camera motion is obtained from the homography matrices. It is very efficient and robust. It works on all data sets that we provided. And once we establish the panorama type, we can choose an appropriate mapping surface, and we can also choose the appropriate bundle adjustment model. And in the future, we would like to publish this data set and obviously extend it a little bit so that we can use it for further research. Okay, are there any questions?
So, I mean, those type of computer vision applications are pretty computationally expensive. So my first question would be, how long does it take on the camera? How much processing does it require? And my other question is, do you need to calibrate your camera beforehand to be able to do these type of things?
Okay, to answer your first question, we made some experiments and measured the time. Actually, you can find it in the paper. It only takes a few seconds, which is still longer than some algorithms that you can find, but I think it's still a reasonable time. To answer the second question, which I forgot now, maybe?
Camera calibration.
Camera calibration, yes. Well, for the rotational panorama, it's not that important to calibrate it, but for the planar panorama, it's very important. When you have a rotational panorama, you can calibrate it during the bundle adjustment process, so that's not a problem, but for the planar panorama, you should do it beforehand.
Any more questions? We have some time.
Yeah, I think the result of the image stitching heavily depends on the quality of the input image set. So what kind of input image set did you use? And then, well, in general, if you have so many input images, then how can you handle the situation?
Okay, so the first question was how can we, or what impact does the image quality have on the image stitching? We have different kinds of panorama input images where most of them are taken in a well-lit environment, so that works well. All of them were taken by smartphones where we all know the quality is not bad, but it's also not the best. So we found that actually the crucial thing is to extract and match the feature points, but when using the SIFT detector, and that works very well. It's very invariant to such changes in illumination or noise, so that can be determined very robustly. We didn't have a problem there. The second question, maybe you can repeat it.
Yeah, if you have so many images and in one place, then you're going to consider all images for the image stitching, then you're going to take lots of time, right?
Yes, that is also a problem that we have, and what we did is we are able to take the images directly on the smartphone and stitch them directly after taking them. So we know in which order the images were taken, and that provides very useful information, so we know how to match what images. So we can actually reduce the complexity of the image matching by knowing which images were neighbors. So that I think most images that we stitched were, I think, 40 or 50 images, so that's a very sufficient number for this task.
Any more questions? Less